Somewhere above the Mozambique Channel, in the black hours before dawn, a storm is doing something it shouldn't be able to do. 2 days earlier, it was falling apart. Its cloud shield had scattered across the hills of central Mozambique. Its winds had dropped to something barely worth naming on a warning bulletin, and the forecasters tracking it from geostationary orbit had all but stopped flagging it as a system of concern. It had already made one landfall, a soft, disorganized hit on the coast north of Beira, dumping heavy rain on villages along the Pungwe River, before drifting inland to die the way almost every tropical system eventually dies, starved of the warm ocean water that built it in the first place. A storm over land is a fire with its fuel line cut. Friction with the ground shreds its low-level circulation. Dry continental air chokes the moisture it needs. And without a source of latent heat to keep its engine turning, it should weaken, fragment, and disappear into an unremarkable line on a weather map, the kind of system meteorologists stop bothering to name in daily briefings. Except this one didn't disappear. It turned around. It crossed back out over the channel, over water that looked, from the deck of any passing fishing boat, like nothing more than the ordinary blue of the tropics, unremarkable, flat, glinting in the pre-dawn light, the way it had for thousands of years before anyone thought to measure it. And within about a day and a half, something in that water fed the storm so completely that its central pressure collapsed. Its eye tightened into a clean, symmetrical circle on satellite loops, and its winds climbed into the range meteorologists reserve for the most dangerous storms on the planet. This was Tropical Cyclone Idai in March of 2019, and what happened next would become one of the worst weather disasters ever recorded in the Southern Hemisphere. Idai made its second landfall almost exactly where it had made its first, near the port city of Beira. But this time it arrived as a far more powerful system, one that pushed a wall of ocean water up the funnel-shaped mouth of the Pungwe estuary and combined it with days of accumulated rainfall pouring down from the highlands of Zimbabwe. Within about 48 hours, satellite images showed an area larger than many small countries submerged beneath a new, temporary inland sea, a body of water so vast that aid workers initially struggled to describe its scale in terms that made sense to people who hadn't seen it directly. Beira, a city of more than 500,000 people, lost roughly 90% of its buildings and infrastructure to some degree of damage. Hospitals lost their roofs mid-storm, with patients and staff sheltering in corridors as wind tore through wards. The airport, the only fast route in or out of the region once roads disappeared beneath floodwater, became the staging ground for a rescue operation that stretched on for weeks, helicopters lifting stranded families from rooftops and treetops across a landscape that had, days earlier, been farmland. More than 1,000 people died across Mozambique, Zimbabwe, and Malawi combined, and well over 1 million more were affected in some direct way. From destroyed homes to wiped-out cropland to weeks without clean water, electricity, or a functioning health system in a region already stretched thin. A cholera outbreak followed within days of the floodwaters receding, spreading through camps of displaced families crowded onto whatever dry ground remained. A grim but predictable second wave of disaster that disaster planners have since folded into how they prepare for the aftermath of major cyclones in this part of the world. In the days that followed, humanitarian workers flying survey missions over the flooded Pungwe and Buzi basins described a landscape that no longer resembled farmland at all, just rooftops and treetops breaking the surface of what had become, temporarily, one of the largest bodies of open water in southern Africa. Roughly comparable in extent to a moderately sized lake formed almost overnight where none had existed before. Fishing boats normally used along the coast were pressed into service far inland, navigating between submerged fields to reach families who had spent days perched on whatever high ground or sturdy structure they could find, rationing what little food and clean water they had managed to save before the flood arrived. International search and rescue teams, coordinated alongside Mozambique's own National Institute for Disaster Management, worked alongside local volunteers who often knew the terrain and the people stranded on it, far better than anyone arriving from outside the region ever could. The combination of outside resources and local knowledge became, in the years since, something disaster planners point to directly when explaining what worked and what didn't during the response. A case study taught well beyond Mozambique's own borders. Watching this unfold on a satellite loop, sped up and played back after the fact, gives a viewer a strange, almost vertiginous sense of watching something come alive. The strange part isn't that a cyclone caused this kind of destruction. Powerful storms have always devastated coastlines, long before anyone kept written records of them. The strange part is the turnaround itself, the way a dying system, reduced to a smear of disorganized cloud, barely holding together on satellite imagery, could sit over a stretch of open ocean for little more than a day and come back as something categorically more dangerous, strong enough to reshape a coastline and end more than 1,000 lives. Meteorologists have a term for this kind of sudden strengthening: rapid intensification, generally defined as a significant jump in maximum sustained winds within a 24-hour window, often on the order of 35 miles an hour or more in a single day, a threshold Idai crossed with room to spare. It happens in ocean basins around the world, but it happens here, in the Mozambique Channel, with a frequency and a violence that has made this particular strip of water one of the most closely watched patches of ocean on the planet, studied by oceanographers and meteorologists trying to understand exactly what makes it behave this way, and by disaster planners trying to figure out how much warning time a coastline like this one can realistically expect to get. Look closely at the timeline and the reversal becomes even harder to explain away as ordinary storm behavior. Idai first crossed the coast north of Beira on roughly the 9th of March as a weak, waterlogged system, the kind of storm that typically earns a brief mention in a regional forecast and nothing more. It spent the following days drifting over Zimbabwe and Malawi, dumping rain but steadily losing whatever structure it had left, to the point that some forecast models briefly stopped tracking it as an organized system at all. Then, in the span of roughly 36 hours, it re-emerged over the channel, reorganized, and struck Beira a second time, on the night of the 14th into the 15th of March, this time as an intense tropical cyclone with a well-defined eye, sustained winds comparable to a major hurricane, and a storm surge that turned the Pungwe estuary into a temporary sea. The World Meteorological Organization would later retire the name Idai from future use in the basin altogether, a formal acknowledgement reserved for storms whose toll was severe enough that reusing the name again would feel, to the communities who lived through it, like a kind of insult. Consider for a moment what that 36-hour window actually looked like from the perspective of a forecaster on duty at the regional center responsible for tracking it. A weakening tropical depression, barely holding together, crosses back over open water in the evening. By the following morning, satellite imagery shows the beginnings of an eye. By that evening, the eye has cleared completely. A stark, dark circle surrounded by a tight ring of the coldest, highest cloud tops the storm can produce. The unmistakable satellite signature of a mature, dangerous cyclone. Warnings that had been quietly downgraded less than 2 days earlier suddenly needed to be reissued at a far higher level of urgency, racing to catch up with a storm that was, by every meaningful measure, now a different system than the one meteorologists had been tracking only hours before. That's the texture of rapid intensification as forecasters actually live it, a compressed, disorienting scramble to communicate a threat that's changing faster than the normal rhythm of forecasting updates was ever designed to handle, playing out across hours, rather than arriving as one dramatic jump captured cleanly on a single satellite image. To understand why, we can't start with the storm. We have to start with what's underneath it in water most people will never see, shaped by currents most people have never heard of. in a channel that behaves less like a passive stretch of sea and more like an engine built, almost by geological accident, to manufacture disaster on a schedule of its own. Look at a map of the Western Indian Ocean, and the Mozambique Channel appears almost as an afterthought, a gap between the African mainland and the long, tilted shape of Madagascar, an island so large that early European navigators sometimes mistook it for a small continent in its own right. The channel stretches roughly 1,000 miles from north to south, narrowing to around 250 miles across at its tightest point near the Comoros archipelago, and widening considerably further north and south, reaching several hundred additional miles across, where it opens into the broader Indian Ocean at both ends. The islands of the Comoros sit almost precisely at that northern pinch point, close enough to both Madagascar and the African mainland that they too sit directly in the path of storms, drawing on the same warm water described throughout this story, a smaller, often overlooked piece of the same hazard picture, usually framed almost entirely around Mozambique itself. To a casual eye, it looks like nothing more than a strait, a piece of geography defined by what surrounds it, rather than by anything happening within it, the kind of body of water a mapmaker might label almost as an afterthought, once the two land masses on either side are drawn in. That impression is almost entirely wrong, and it's worth pausing on just how easy it is to form that wrong impression in the first place. Most people encounter the Mozambique Channel, if they encounter it at all, as a thin blue sliver on a world map, or a brief mention in a news report about a storm making landfall somewhere along its edges. Nothing about that kind of glancing exposure suggests that this stretch of water hosts a current system studied intensely enough to have generated dedicated oceanographic field campaigns, doctoral research programs, and international collaborations stretching back decades. The channel's danger is, in this sense, doubly hidden beneath the ocean surface in the form of subsurface heat most people never think to consider, and hidden behind a visual impression, the thin gap on a map, that actively discourages anyone from suspecting there's more going on underneath. The channel sits at a genuine crossroads of ocean circulation, one of the more complex current systems found anywhere in the southern hemisphere. To its east, the warm waters pushed south and west by the persistent trade winds split around the northern tip of Madagascar as part of the broader South Equatorial Current, sending one branch down the island's eastern coast as the East Madagascar Current and another branch curling west into the channel itself, squeezing through a relatively narrow gap between Madagascar's northern tip and the coast of Mozambique. To its south, the channel feeds directly into the beginning of the Agulhas Current, one of the strongest and most intensely studied ocean currents in the world, a river of warm water carrying an extraordinary volume of heat that eventually races down the east coast of South Africa before famously curling back on itself in a phenomenon called the Agulhas retroflexion, one of the more striking examples anywhere on Earth of an ocean current essentially turning around and flowing back the way it came. The Agulhas system matters far beyond the waters immediately off southern Africa. Oceanographers studying global heat transport have documented a process known as Agulhas leakage, in which warm, salty rings of water pinch off from the retroflexion and drift westward into the South Atlantic, carrying heat and salt that ultimately influence the strength of ocean circulation patterns spanning the entire Atlantic basin. The Mozambique Channel, sitting upstream of all of this, functions as one of the feeder systems for a current whose influence extends thousands of miles beyond the channel itself, which is part of why the region has attracted sustained scientific attention from institutions well beyond Mozambique and South Africa, including oceanographic research programs based in Europe and the United States that have run dedicated field campaigns in these waters specifically to understand how heat moves through this system. One notable regional effort supported by international development funding and coordinated across multiple countries bordering the Western Indian Ocean spent years deploying moored instruments and conducting research cruises specifically to improve understanding of the currents feeding this stretch of ocean, work that fed directly into the kind of eddy tracking and heat content mapping described throughout this story. None of this research exists purely for its own sake. Every improvement in understanding how the channel's eddies form, drift, and interact with passing storms translates eventually into better guidance for the forecasters and disaster planners working on the coastlines those storms threaten. For a long time, none of this internal structure was visible to anyone. Sailors crossing the channel for centuries noted its currents empirically, the way sailors always have, adjusting their routes based on which way the water seemed to be pulling them. But the idea that the channel hosted a whole population of enormous, independently drifting rings of warm water wasn't confirmed until oceanographers gained the ability to measure sea surface height from orbit, with enough precision to detect the subtle bulge of water sitting atop a warm core eddy, typically only a matter of inches higher than the surrounding sea, but enough to reveal an entire hidden architecture of circulation once decades of satellite passes were stitched together into a continuous record. What sailors had always described as unpredictable, shifting currents turned out to be the visible surface signature of a population of enormous, drifting heat reservoirs moving beneath their hulls the entire time. Far from a dead end, the channel functions as a conduit, a place where warm equatorial water is funneled, twisted, and recirculated before being released further south into that larger Agulhas system. And because of the particular geometry of that funneling, shaped by the narrow gap at the channel's northern entrance and the long, gradually widening basin to its south, the channel does something unusual with its heat. Instead of moving warm water through in a smooth, steady current, the way you might picture a river flowing downhill between two banks, the inflow breaks apart into a chain of enormous rotating rings of water, each one hundreds of miles across, spinning slowly southward over a period of months like a loose string of pearls drifting down the length of the channel. These rings, known to oceanographers as mesoscale eddies, aren't a minor curiosity buried in an academic paper somewhere. The Mozambique Channel produces some of the most energetic eddy activity found anywhere in the global ocean, a fact confirmed repeatedly once satellites capable of measuring sea surface height began systematically observing the region in the 1990s, revealing a pattern of circulation so distinctive that oceanographers now refer to it, somewhat informally, as the Mozambique Channel Eddy Train. Research institutions across several continents have since built dedicated programs around studying it, including university and government oceanography departments in South Africa, France, and Mozambique itself, often collaborating on joint field campaigns and shared datasets, since no single country's research fleet could realistically monitor a current system this large and this dynamic entirely on its own. Graduate students have built entire careers charting the birth, drift, and dissolution of individual eddies within this channel, work that decades ago would have seemed like an obscure academic pursuit, but that now sits directly upstream of operational cyclone forecasting for millions of people living along the coasts it affects. Each of these spinning rings carries a signature that matters enormously to what happens overhead in the atmosphere months or even a full year later. A single number on a sea surface temperature map, the kind shown on a nightly news broadcast during cyclone season, tells you almost nothing about what's happening beneath the surface. Two patches of ocean can show the exact same reading on a thermometer, both comfortably warm enough by any standard measure to support a tropical cyclone, and behave completely differently once a storm arrives, because what actually matters isn't how warm the very top layer of water is. What matters is how far down that warmth extends and how much energy sits stored in the layer beneath the surface, quietly, invisibly, waiting for something above it to draw on it. That distinction, buried a few hundred feet below the waves, where no satellite camera and no casual observer can see it directly, turns out to be the real story of why this channel builds monsters while other, Seemingly identical patches of tropical ocean nearby produce only ordinary storms. It helps to picture the difference the way an oceanographer might sketch it on a whiteboard. Imagine two swimming pools sitting side by side on a hot afternoon, both heated to the exact same comfortable temperature at the surface. One pool is shallow, only waist deep, with cold groundwater seeping in just beneath that thin, warm layer. The other is enormously deep, its warmth extending far below where any swimmer could touch bottom. Stir the shallow pool vigorously with a paddle, and you will quickly drag up the cold water hiding just beneath the surface, cooling the whole pool within minutes. Stir the deep pool with the same paddle, just as vigorously, and the warmth barely changes, because there's so much of it stacked below that no amount of surface agitation can reach down far enough to disturb it. A tropical cyclone is, in this sense, nothing more than an extraordinarily powerful paddle, and the Mozambique Channel's eddies are what turn an ordinary shallow pool of warm water into the deep one. Long before satellites or oceanographers took any interest in this channel, it was already central to the economic life of the communities along its shores. Small-scale fishing fleets from Mozambique, Madagascar, and the Comoros have worked these waters for generations, following the same seasonal patterns of current and upwelling that oceanographers now describe with satellite data and moored instruments. The channel supports coral reef systems along both coastlines, seagrass meadows that serve as nurseries for fish stocks the region depends on, and populations of dugongs and marine turtles found in few other parts of the western Indian Ocean in comparable numbers. That same biological richness sits directly downstream of every cyclone that crosses the channel, meaning the storms described throughout this story carry an ecological cost layered directly on top of the human one. Severe cyclones can scour seagrass beds, bury coral reefs under sediment washed out from flooded rivers, and disrupt fish spawning cycles for seasons afterward, a toll that compounds the human one, and that takes considerably longer to recover from than a rebuilt seawall or a repaired road. Madagascar's own western coastline, facing directly into the channel, carries a parallel version of every hazard described so far for Mozambique, though it receives far less international attention when disaster strikes. Storms crossing the channel frequently make landfall on Madagascar first, weather weakening over the island before reorganizing toward Mozambique, as Idai and Freddy both did in different ways, or striking Madagascar directly as their primary target. Coastal communities along Madagascar's west coast face many of the same compounding hazards as Mozambique's Sofala coast: seasonal flooding, limited infrastructure, and a heavy reliance on agriculture and fishing for daily survival, even though most global coverage of this channel's storms tends to focus overwhelmingly on whichever landfall produced the highest death toll, usually on the mainland side. Set the geography and the communities aside for a moment and look at the storm itself, stripped down to what it actually is. Every tropical cyclone is, at its core, an engine built to move heat from the ocean into the atmosphere. Warm surface water evaporates. That water vapor rises and condenses into towering thunderstorms, wrapping around a developing center of low pressure, and the process of condensation releases enormous amounts of latent heat, energy, that had been absorbed from the sun and stored invisibly in the water for weeks or months, which in turn drives the winds that spiral inward and upward around the storm's core. The whole system runs on a single input, heat pulled continuously from the sea, and the entire structure of the storm, from its outer rain bands to its tightly wound eye wall, exists essentially to move that heat as efficiently as possible from ocean to atmosphere. The eye itself, the deceptively calm center that gives a mature cyclone its recognizable satellite image, forms almost as a mechanical byproduct of this process rather than as some separate feature. As air spirals inward and upward through the eye wall with increasing speed, it begins to conserve its angular momentum the way a spinning ice skater speeds up by pulling their arms inward, and at a certain radius from the storm's center that spin becomes strong enough to fling air outward rather than inward, carving out a relatively calm, sinking column of air at the very center where the surrounding eye wall's fierce winds can't reach. Meteorologists reading satellite imagery treat the clarity and symmetry of this eye as one of the more reliable visual indicators of a storm's strength. A small, tightly wound, clearly defined eye typically signaling a far more powerful and well-organized system than a broad, ragged, poorly defined one, which is part of why Idai's transformation over the Mozambique Channel, from a formless smear of cloud to a storm with a textbook clean eye within a day and a half, read so unmistakably as a warning sign to anyone watching the satellite loop in real time. For decades, meteorologists used a rough rule of thumb to explain where cyclones could form at all. Sea surface temperature needed to sit at roughly 26.5 degrees Celsius or warmer, a threshold first popularized by early tropical meteorology research in the middle of the 20th century. And that rule does a reasonable job of explaining where tropical cyclones can form in the broadest possible sense, sketching out the general tropical belt where warm enough water exists somewhere in the world at any given time of year. But it does a poor job of explaining why some storms sit over water that comfortably clears this threshold and barely strengthen at all, drifting along as disorganized weak systems for days, while others sit over water reading almost identically on a thermometer and explode into major storms within a single day. The missing piece is depth, and it took oceanographers and meteorologists decades of dedicated research, much of it advanced significantly by hurricane scientists studying the Gulf of Mexico's loop current, to fully appreciate just how much that missing piece actually mattered. Picture a tropical cyclone's winds churning the ocean's surface as it moves across the water. That churning does more than whip up waves visible from a boat or a beach. It physically mixes the water column beneath the surface, dragging cooler water up from below and blending it with the warm surface layer the storm depends on. In most parts of the tropical ocean, that cooler water sits uncomfortably close to the surface, maybe only a few dozen feet down, separated from the warm surface layer by a sharp boundary called the thermocline, a zone where temperature drops rapidly over a relatively short vertical distance. When a storm's winds stir that boundary, cold water rises toward the surface. The sea surface temperature directly beneath the storm drops, sometimes by several degrees within hours, visible clearly in satellite imagery as a trailing cold wake stretching out behind the storm's path, like a scar left on the ocean's skin. The storm effectively begins choking off its own fuel supply the moment it starts working hardest. This self-limiting feedback is one of the main reasons most tropical cyclones on Earth never reach anything close to their theoretical maximum intensity. The storm builds its own brake pedal directly into the system by disturbing the very water it depends on to survive. Now picture a different setup, one where that thermocline isn't sitting a few dozen feet down but has been pushed down several hundred feet, so that warm water extends far deeper than usual before any meaningful cooling begins. A storm can churn that same ocean surface just as violently as it would anywhere else, generating the same waves, the same visible turbulence. But because the reservoir of warm water underneath is so much deeper, the churning can't reach down far enough to drag up meaningfully colder water. No self-inflicted break exists here. No cold wake trailing behind to slow the storm's progress. The storm keeps drawing on a heat supply that refuses to run cold, no matter how hard it works. And under the right atmospheric conditions overhead, it intensifies with a speed that looks, from a satellite loop played back at normal speed, almost unnatural, an eye tightening and clearing within a matter of hours rather than days. Hurricane researchers sometimes describe this distinction using the shorthand of a shallow ocean environment versus a deep ocean environment, a simplification that captures the practical stakes without requiring a forecaster to recite the full oceanographic detail every time a storm's outlook needs updating. A shallow environment caps a storm's potential regardless of how warm its surface reading looks on a given afternoon. A deep environment removes that cap almost entirely, handing a storm a runway toward its full theoretical potential, limited mainly by the atmosphere above it, rather than the ocean below it. This second setup, deep warm water resistant to storm-driven mixing, is exactly what the Mozambique Channel's eddies create, and it's precisely what fed Idai during its final day and a half over open water. Each rotating ring of water, spun off from the confluence of currents at the channel's northern entrance, depresses the thermocline beneath it by anywhere from several dozen to well over 300 feet, depending on the eddy's strength, size, and age at the moment a storm happens to cross it. Oceanographers measure this property directly using a metric called tropical cyclone heat potential, sometimes referred to as ocean heat content, which accounts for the full depth of warm water down to a reference temperature rather than just the surface reading a casual observer or a basic weather map would show. Studies of the channel using data collected from satellite altimetry combined with a global network of autonomous ocean profiling floats, instruments that drift with the current, while periodically diving to measure temperature and salinity at depth before surfacing again to transmit their data by satellite, have repeatedly found some of the highest heat potential values recorded anywhere in the southern hemisphere, sitting directly beneath these eddies, values that can rival or exceed conditions found in the warmest parts of the western Pacific. The ocean basin, most associated in the public imagination with monster storms. The satellite record behind these measurements is itself a small scientific achievement worth pausing on. Beginning with a mission launched jointly by the United States and France in the early 1990s, and continued by a succession of follow-on satellites carrying increasingly precise radar altimeters, oceanographers have been able to measure the height of the sea surface from orbit to a precision of just a couple of inches, repeated across the same patch of ocean every few days for more than 3 decades running. That continuous, decades-long record is what eventually allowed researchers to distinguish a genuine, recurring population of warm core eddies in the Mozambique Channel from ordinary short-term noise in the data, and it's combined today with a global fleet of several thousand autonomous profiling floats drifting freely with the current across every ocean on Earth, periodically sinking to a depth of roughly a mile before rising back to the surface over the following days, measuring temperature and salinity the entire way up before radioing their findings home. Without this combination of instruments, the deep warm water beneath a Mozambique Channel eddy would remain exactly what it was for most of human history, an invisible, unmeasured hazard sitting beneath an ocean surface that looked, to any observer on a boat, like nothing more than warm, calm water. Researchers who study rapid intensification events around the world have proposed rough threshold values for tropical cyclone heat potential, above which the odds of a storm undergoing this kind of explosive strengthening rise sharply, values well above what the old, surface-only rule of thumb would suggest is even necessary for ordinary cyclone formation. The Mozambique Channel's eddies frequently push heat potential in the water column well past those thresholds during the height of cyclone season, which is precisely why a storm crossing a mature eddy here behaves so differently from a storm crossing an equivalent patch of merely warm, shallow water elsewhere in the tropics. That's the first piece of the puzzle, and it reframes the entire premise of the question at the center of this story. The Mozambique Channel isn't simply warm. Warm surface water alone is common across huge stretches of the tropical ocean and produces plenty of unremarkable slow strengthening storms that never make international headlines. What makes this channel different, what makes it worth singling out from among dozens of other tropical waters around the world, is that its eddy field routinely stacks up deep reservoirs of stored heat, pockets of ocean that behave, from a storm's perspective, like a fuel tank with no bottom, refilling itself faster than the storm above it can ever hope to drain it. To understand how these eddies form, it helps to trace the water back to its source, following the same path a molecule of seawater might take over the course of a year or more as it travels from the open equatorial Indian Ocean into the Channel and eventually out again. Along the eastern coast of Madagascar, the South Equatorial Current, pushed by persistent trade winds blowing from the southeast across thousands of miles of open ocean, strikes the island and splits. Part of that current bends south along Madagascar's eastern shoreline as the East Madagascar Current, gathering warmth from months spent sitting under equatorial sun before eventually rounding the island's southern tip. From there, instead of flowing smoothly and continuously into the open Indian Ocean, a portion of this warm water gets pulled westward and northward, drawn into the Mozambique Channel through the narrow gap at its southern end near Madagascar's southwestern coast, before working its way slowly north within the channel itself. What happens next is what oceanographers describe as an unusually energetic, counterintuitive circulation pattern, one that took decades of satellite observation to properly document because it doesn't behave the way a simple river-like current would. Rather than settling into a single, continuous current running the length of the channel, from north to south, the water organizes itself into a semi-regular procession of enormous anticyclonic rings, essentially self-contained whirlpools of warm water, each one forming near the channel's northern mouth roughly every couple of months and then drifting slowly south along the Mozambican coast over a period of several months, sometimes taking the better part of a year to traverse the full length of the channel before dissipating into the surrounding water or merging into the Agulhas current system further south, where its remaining heat gets absorbed into that much larger and better-known current. Each of these rings is, in effect, a mobile reservoir of stored heat, hundreds of miles wide, carrying warm water pulled down to unusual depths by the physics of its own rotation. An anticyclonic eddy, spinning clockwise in the southern hemisphere, exactly opposite the direction a low-pressure storm system spins in the same hemisphere, forces water toward its center through a process oceanographers call downwelling, which is precisely what pushes the thermocline deeper beneath the eddy's core, sometimes by hundreds of feet compared to the surrounding water only a short distance away. As this ring drifts south, month after month, it effectively drags a pocket of deep, warm water along the length of the Mozambican coastline, a moving target that shifts positions from year to year and even month to month depending on how the eddies happen to be spaced and timed in any given season, sometimes clustering closer together, sometimes spreading further apart, in patterns that remain only partially predictable more than a few months in advance. This matters enormously for storm forecasters because it means the danger zone within the channel isn't fixed in place the way a reef or a shoal might be. A cyclone track that would have passed harmlessly over cooler, shallower warm water in one season might, a year later, cross directly over the deep, sun-warmed core of a mature eddy, sitting in a slightly different position, with drastically different consequences for how the storm behaves in its final approach to the coast. Researchers studying the region, drawing on decades of satellite altimetry data cross-referenced against the historical track and intensity record of cyclones crossing the channel, have found a clear statistical relationship between the presence of these warm core eddies and episodes of rapid intensification, to the point where tracking eddy position and depth has become a meaningful part of operational forecasting for the region, discussed alongside more traditional atmospheric variables like wind shear and humidity in the technical bulletins issued by regional forecasting centers during active storms. Research teams studying the channel have gone so far as to individually track specific eddies across their entire lifespan, following a single ring of water from the moment it pinches off near the channel's northern entrance, through its months-long southward drift, to the point where it finally dissolves into the Agulhas system, much the way meteorologists track an individual cyclone from formation to dissipation. These studies have revealed that eddies vary considerably in strength and longevity from one year to the next, with some seasons producing a tightly spaced sequence of powerful, long-lived rings, and other seasons producing a weaker, more sporadic field variability, that appears to be only loosely connected to broader climate patterns, like the same El Niño cycle that influences Atlantic hurricane activity, and that remains, even now, one of the harder aspects of the channel's behavior to forecast more than a season in advance. Something almost unsettling sits inside this mechanism once you spend a moment with it. The ocean isn't a static backdrop against which storms happen to occur, the way it's sometimes casually described, a passive stage on which the real drama of weather plays out overhead. In the Mozambique Channel, it's an active, shifting, semi-independent system, one that builds and relocates its own hazards on a timescale of months, largely invisible from the surface to anyone without access to satellite data, silently setting the stage for whichever storm happens to wander across the right patch of water at the right moment in its life cycle. A cyclone crossing the channel is doing something far more specific than merely encountering warm water in some generic sense, the way a summary weather report might describe it. It may be crossing directly over a specific, identifiable ring of anomalously deep heat that formed months earlier near Madagascar's northern coast and has been quietly drifting south ever since, entirely on its own schedule, waiting for a storm to arrive. The Agulhas Current, waiting at the channel's southern exit, has its own long history of violence entirely separate from tropical cyclones, one that gives some sense of just how much raw energy moves through this stretch of ocean, even outside cyclone season. Mariners rounding the southern tip of Africa for centuries describe the waters there as some of the most treacherous on Earth, a reputation that eventually earned the nearby headland the name it still carries in navigational charts today, associated more with storms and shipwrecks than with any calm passage. Modern oceanographers have since documented the physical reason behind that old reputation. When the Agulhas Current's swift southward flow runs directly against powerful southwesterly swells generated by storms further south, the opposing forces can build so-called rogue waves, walls of water far taller than the surrounding sea state would predict, capable of snapping the hull of a large cargo ship in open water. That's a useful reminder that the Mozambique Channel doesn't exist in isolation. It sits at the head of a current system whose power downstream has been feared and studied for centuries, long before anyone connected it to the separate but related question of why cyclones passing overhead behave the way they do. Before turning to the specific atmospheric ingredients that make the Mozambique Channel unusual, it helps to understand why a rotating storm needs to be anywhere near the tropics at all, rather than simply forming wherever warm water happens to exist. A tropical cyclone's rotation is set in motion by the Coriolis effect, a consequence of the Earth's own spin that deflects moving air to the left of its path in the southern hemisphere and to the right in the northern hemisphere, which is why cyclones spin clockwise south of the equator and counterclockwise north of it. That deflection is essentially non-existent directly at the equator and strengthens gradually with distance from it, which is why tropical cyclones almost never form within a few degrees of latitude of the equator itself, no matter how warm the water there might be. The Mozambique Channel sits comfortably within the latitude band, where this effect is strong enough to organize rotation efficiently. Another quiet precondition, rarely mentioned alongside sea surface temperature, that has to be satisfied before any of the ocean heat described earlier can actually be put to use. Once a storm does organize, its most dangerous transitions often happen inside a structure called the eye wall, the ring of the most intense thunderstorms, circling the calm center of the storm. Strengthening cyclones frequently undergo what meteorologists call an eye wall replacement cycle, in which an outer ring of thunderstorms forms around the original eye wall, gradually chokes off its inflow of warm, moist air, and eventually replaces it as the storm's primary engine, typically causing a brief pause or even a temporary weakening in the storm's winds before the new, often larger eye wall stabilizes and the storm resumes strengthening, sometimes to a higher peak intensity than before. That's one of several reasons a storm's intensity can appear to fluctuate, even while it sits over ideal conditions the entire time. And it's one of the structural details forecasters watching Mozambique Channel storms have to account for when trying to anticipate a system's next move. Since a temporary lull in reported winds doesn't necessarily mean the storm's underlying environment has become any less favorable. Warm water alone doesn't make a hurricane or a cyclone or a typhoon, depending on which ocean basin you happen to be standing in when you name it. The atmosphere has to cooperate too, and the Mozambique Channel's location, tucked between the tip of southern Africa and the tilted length of Madagascar, grants it a set of atmospheric conditions almost as unusual as its ocean structure. Conditions that shift with the seasons in a pattern reasonably well understood by climatologists studying the broader southwest Indian Ocean region. The channel's cyclone season runs roughly from November through April, a window dictated by the seasonal migration of the intertropical convergence zone, the broad band of rising moisture-laden air that circles the globe near the equator and shifts north and south with the changing angle of the sun through the year, dragging the belt of heaviest tropical rainfall along with it. During the southern summer, this convergence zone, along with an associated feature called the monsoon trough, a corridor of low pressure and converging surface winds, migrates south over the Mozambique Channel and the surrounding waters, bringing with it the kind of persistently moist, unstable atmosphere that tropical cyclones need to organize in the first place. An atmosphere thick with the kind of humidity that allows towering thunderstorms to build and sustain themselves for hours or days at a stretch. Outside this window, the same waters that produce monsters in February are largely left alone. Not because the ocean beneath them changes dramatically in temperature during the intervening months, but because the atmosphere above it withdraws its cooperation as the convergence zone retreats north again. Low vertical wind shear ranks among the 2 or 3 atmospheric ingredients a developing cyclone needs most, meaning winds at different altitudes, from near the surface up through the middle and upper atmosphere, blowing at roughly similar speeds and from roughly similar directions. When upper-level winds differ sharply from winds near the surface, they tilt a developing storm structure, tearing its rising columns of thunderstorms away from its center of low pressure before they can properly organize, and preventing the kind of tight, symmetrical eye that allows for genuine strengthening. High shear kills more developing storms than any other single factor in any ocean basin on Earth, capable of unraveling even a well-developed system within a day or two. And it's one of the main reasons meteorologists watch shear forecasts as closely as they watch sea surface temperature maps when trying to anticipate how a storm will behave over the coming days. During the heart of the Mozambique Channel's cyclone season, shear across the region frequently drops into a favorable range, particularly when broader climate patterns align in the storm's favor. The Madden-Julian Oscillation, a slow-moving pulse of enhanced and suppressed thunderstorm activity that circles the globe near the equator over a period of roughly a month to 6 weeks. First identified by meteorologists in the 1970s and studied intensively ever since, plays a well-documented role here. When the active phase of this oscillation passes over the southwest Indian Ocean, it tends to suppress wind shear and enhance the deep, moist convection that cyclones need to organize, essentially opening a temporary window of favorable conditions that can last anywhere from a week to several weeks. And forecasters have observed a clear clustering of intense cyclone activity in the Mozambique Channel during these favorable windows, with multiple storms sometimes forming or intensifying in close succession once the pattern turns favorable, only for activity to quiet down again once the oscillation's active phase moves on to another part of the globe. A second, slower climate pattern layers on top of the Madden-Julian Oscillation's faster rhythm, the Indian Ocean Dipole, a basin-wide seesaw in sea surface temperature between the western and eastern Indian Ocean that shifts phase over a period of many months to roughly a year, broadly comparable in structure, though not in mechanism, to the more widely known El Niño pattern in the Pacific. During what climatologists call a positive phase of this dipole, waters in the western Indian Ocean, including the approaches to the Mozambique Channel, tend to run warmer than average, while the eastern Indian Ocean runs cooler, a configuration that has been statistically linked to more active cyclone seasons across the southwest Indian Ocean basin as a whole. Forecasters and climate researchers watching this basin track the dipole's phase alongside the Madden-Julian Oscillation and the more familiar El Niño cycle in the Pacific, since all three patterns interact, sometimes reinforcing each other's effect on the channel's atmosphere and sometimes working against one another, adding yet another layer of variability that makes any single cyclone season difficult to forecast with confidence more than a few months ahead of time. The monsoon trough itself doesn't always produce a single, isolated storm at a time. During particularly active windows, the same corridor of low pressure and converging winds that spawns one cyclone can, within days, spin up a second disturbance elsewhere along its length, occasionally leading to two or more systems developing simultaneously across the broader southwest Indian Ocean basin, one perhaps tracking through the Mozambique Channel, while another develops further east near Mauritius or Reunion. Forecasters at the Regional Center on Reunion Island have, in especially active seasons, found themselves issuing bulletins on multiple named storms at once, stretching the limited satellite and staffing resources available to the basin across more simultaneous threats than any single team would ideally want to track, a logistical strain that compounds the observational challenges described later in this story. A second atmospheric factor is worth understanding here, one that operates far above the storm itself, well beyond what any observer on the ground, or even most satellite imagery, would immediately notice. Tropical cyclones need somewhere for the air they draw in at the surface to go once it rises through the storm's core and reaches the upper atmosphere. If that rising air can't escape efficiently at high altitude, it piles up above the storm, chokes its internal circulation, and caps its intensity. In much the same way a chimney with a blocked flue smokes up a room instead of drawing air cleanly upward and out. Meteorologists call this outflow, and the presence of an upper-level channel for that outflow to escape into, often assisted by the position of the subtropical jet stream, and associated features of the upper atmosphere, including transient troughs and ridges that shift from week to week, is just as critical to a storm's ultimate intensity as the fuel supply below it in the ocean. The Southwest Indian Ocean, during the height of cyclone season, frequently provides exactly this kind of efficient upper-level exhaust system, particularly for storms tracking through the relatively narrow confines of the Mozambique Channel itself, where the surrounding geography seems to help funnel outflow patterns in a way that larger, more open ocean basins don't always replicate as consistently. Put these atmospheric ingredients together with the ocean's deep, eddy-driven heat reservoirs described earlier, and you get a genuinely rare combination. One meteorologists studying this specific basin have spent considerable effort trying to characterize precisely. No single ingredient found in the Mozambique Channel is unique to this stretch of ocean in isolation. Favorable wind shear exists elsewhere, at various points throughout the year in ocean basins around the world. Deep warm water exists elsewhere, most notably in the Gulf of Mexico's Loop Current and the Western Pacific's Warm Pool. Efficient upper-level outflow exists elsewhere too, wherever the broader pattern of upper atmospheric winds happens to cooperate. What's comparatively rare, and what makes the Mozambique Channel worth this level of scientific attention, is finding all three stacked reliably together, season after season, over a channel narrow enough that a storm forming anywhere within, it's virtually guaranteed to encounter this full combination rather than drifting past it or through only part of it, the way a much larger storm crossing a broader ocean basin might spend only a portion of its life under genuinely ideal conditions before moving into less favorable water or atmosphere. The story so far explains why cyclones intensify explosively over the Mozambique Channel's open water. It doesn't yet explain why that intensification turns so catastrophic once these storms reach land, and for that, the answer moves from water and sky down to the shape of the seafloor itself, a feature of geography easy to overlook because it's quite literally invisible from the surface. Along much of the Mozambican coastline near Beira and the mouth of the Pungwe and Buzi rivers lies a feature known as the Sofala Bank, one of the widest and shallowest stretches of continental shelf found anywhere along Africa's eastern coastline. Buon Iwal Wernananaisikin, formed over thousands of years by sediment carried down from the highlands of the interior by exactly the same rivers that flood the region during major storms today, including not only the Pungwe and Buzi, but also the much larger Zambezi, whose mouth sits only a short distance up the coast, and whose delta has, over geological time, deposited enormous volumes of sediment that helped build out the shallow shelf running past Beira in the first place. In effect, the very rivers whose floodwaters compound a cyclone storm surge today are the same rivers that spent thousands of years constructing the shallow seabed responsible for amplifying that surge, a geological feedback loop connecting river and coastline that long predates any storm, any city, or any person who has ever lived along this stretch of Africa's eastern edge. Where many coastlines drop off relatively quickly into deep water just offshore, the seabed here stays shallow for a long distance out to sea, in places extending the shallow shelf more than 60 miles from the coast before reaching significant depth. A gently sloping underwater plain that fishing communities along this coast have navigated for generations, using knowledge passed down about where the shallows begin and end. This geometry acts as a kind of amplifier for storm surge, the wall of ocean water that tropical cyclones push ahead of themselves as their winds pile water toward the coast over the course of hours or days as the storm approaches. Over deep water, a cyclone surge has room to spread and disperse across a large volume of ocean before it ever reaches shore, the piled-up water able to flow outward and downward into the depths, rather than being forced to go anywhere in particular. Over a long, shallow shelf, that same volume of pushed water has nowhere to go but up, compressed into an ever-shrinking wedge of shallow sea as the storm approaches land, arriving at the coastline as a far higher, more destructive wall of water than the storm's wind speed alone would suggest to anyone reading only a category rating on a warning bulletin. That's a well-understood principle in coastal meteorology, sometimes described using the analogy of a bathtub effect, and it's a major reason why cyclones striking shallow, gently sloping coastlines, from the northern Gulf of Mexico to the Bay of Bengal to Mozambique's Sofala coast, tend to produce disproportionately deadly storm surges compared to their counterparts striking steep, deep-water coastlines elsewhere. Even when the storms themselves carry similar wind speeds at landfall, the same amplifying geometry has been documented and studied closely along the Gulf Coast of the United States, most notably in and around New Orleans, a city built below sea level and surrounded by a similarly shallow, gradually sloping shelf that helped turn Hurricane Katrina's storm surge in 2005 into one of the most destructive in American history, breaching levees and flooding roughly 80% of the city itself. Engineers and coastal scientists studying that disaster developed much of the modern understanding of how shallow shelf geometry amplifies surge height, research that has since been applied, with local adaptations, to other vulnerable, shallow shelf coastlines around the world, including the stretch of Mozambique's coast around Beira, even though the underlying storms themselves, an Atlantic hurricane feeding off the Gulf's loop current versus an Indian Ocean cyclone feeding off the Mozambique Channel's eddy train, form through broadly the same physical process described earlier in this story. One related phenomenon is worth naming as well: wave setup, a secondary effect layered on top of storm surge in which the sheer volume of breaking waves arriving continuously at a shallow shoreline, physically raises the average water level further still, sometimes by several additional feet beyond what surge alone would produce, an effect that becomes especially pronounced exactly where a wide, shallow shelf allows waves to remain large and powerful right up until they reach the coast, rather than losing much of their energy to friction against a longer stretch of shallow seabed, the way they would along a more gradually sloping, wave-dissipating shoreline. A simple picture explains why shallow water amplifies a surge instead of absorbing it. Picture a garden hose with water running through it at a steady rate. Esquesten kichurhaint. Squeeze the open end down to a narrower opening, and the water doesn't slow to match the narrower space. It speeds up and sprays higher, because the same volume of water is being forced through a smaller opening in the same amount of time. A storm surge crossing a wide, shallow shelf behaves in a related way. The volume of water the storm's winds are pushing toward shore stays roughly constant, but the space available for that water to occupy keeps shrinking as the seabed rises toward the coastline, and the water has nowhere left to go except upward, arriving on shore as a taller wall than it would have formed over a steep, deep-water coastline where the same volume of pushed water could spread out across far more depth, right up until the moment it reached land. Beira sits almost precisely where this shallow bank meets the funnel-shaped mouths of two rivers, the Pungwe and the Buzi, both of which drain extensive inland catchments across central Mozambique and stretching into eastern Zimbabwe, gathering rainfall from a drainage area, covering tens of thousands of square miles, before channeling it back toward the coast. When Cyclone Idai's surge pushed inland in March of 2019, it didn't simply flood a beachfront the way a storm might along a straighter, less complicated coastline. It drove seawater up these river mouths, meeting a simultaneous surge of fresh water flowing the opposite direction from days of torrential rainfall dumped across the highlands upstream, water that had nowhere to drain because the sea itself was pushing back against it. The two forces met almost directly over the city and its surrounding lowlands, a combination that hydrologists and disaster researchers have since pointed to as one of the defining reasons Idai's flooding proved so catastrophic and so difficult to predict using storm surge models built primarily around coastal geometry alone, without fully accounting for simultaneous river flooding arriving from the opposite direction at nearly the same moment. That's worth sitting with for a moment, because it reframes what a storm surge disaster actually is in a place like this. Ocean water and river water converge on the same low-lying ground from opposite directions at nearly the same moment, a pincer effect made possible by the specific shape of this stretch of coastline, far more complex than the simple image of ocean water arriving at a beach that the term storm surge usually conjures, and largely invisible to anyone looking only at wind speed categories on a warning bulletin issued days before landfall, when the storm's final track and the state of upstream rainfall are still uncertain enough that this compound effect can be difficult to forecast with real precision. One bureaucratic detail behind every storm name mentioned in this story is worth understanding, because it says something about how genuinely regional this hazard is. Names for tropical cyclones in the southwest Indian Ocean aren't assigned by any single country. They're drawn from lists proposed collectively by the National Meteorological Services of the countries the basin affects, including Madagascar, Mauritius, the Comoros, and Mozambique itself, cycling through in order as storms form each season, with the formal authority to declare a system's official name resting with the specialized centers on Mauritius and Madagascar, working in coordination with the regional center on Reunion Island. That shared naming process reflects a broader truth about this basin. No single nation experiences the Mozambique Channel's hazards in isolation, and no single nation's meteorological service, however well-resourced, could realistically monitor this stretch of ocean alone. The forecasting effort described throughout this story, patchy and under-resourced as it often is compared to wealthier basins, is nonetheless a genuinely cooperative one, built on shared data and shared responsibility across a group of countries that, individually, have comparatively few resources to spare but that have found, out of necessity, a way to pool what they do have. None of this is theoretical. The Mozambique Channel has produced a documented sequence of storms over the past several decades that reads almost like a slow-motion demonstration of every mechanism described so far, each one adding another layer to what scientists and disaster responders now understand about this particular stretch of ocean, and each one leaving behind a body of data that researchers have gone on to study in detail. Cyclone Eline, in February of the year 2000, arrived after weeks of already unusual rainfall had left much of southern Mozambique saturated, and its rivers running high, the ground so waterlogged that even moderate additional rainfall was already producing localized flooding before the storm itself arrived. Eline crossed the full width of Madagascar, weakened as expected over the island's mountainous terrain, and then, much like Idai would 19 years later, reorganized rapidly once it reached the warm water of the channel, striking central Mozambique as a powerful storm that combined with the already swollen Limpopo River to produce flooding across an enormous stretch of the country's lowlands. Entire towns disappeared beneath the floodwaters for days, with rescue helicopters plucking stranded families from rooftops and from the branches of trees, images that were broadcast around the world and that for many people outside the region marked the first time they had ever heard of Mozambique's particular vulnerability to this kind of disaster. The Eline disaster killed several hundred people and displaced hundreds of thousands more, and it remains, alongside Idai, one of the reference points Mozambican disaster planners still use when describing worst-case flood scenarios for the region, a benchmark against which every subsequent major storm gets measured. One detail from that disaster still circulates among people who study the region's flood history. Rescue crews searching the flooded Save River Basin found a woman who had given birth in a tree while waiting days for help to arrive. Both mother and newborn eventually lifted out by helicopter, an image that came to stand, for many people who otherwise knew little about Mozambique, as a symbol of both the disaster's scale and the sheer determination required to survive it. Eline wasn't an isolated case even within its own era. Cyclone Favio, in February of 2007, followed a broadly similar path, tracking across the channel and striking central Mozambique with hurricane-force winds after a period of intensification over open water, while Cyclone Jacques, in March of 2008, brought damaging winds and flooding to the northern part of the country. Neither reached the scale of Eline or later Idai, but both added to a growing body of case studies that researchers use to refine early statistical models of how storms crossing this channel tend to behave, models that decades later would still only partially capture the speed at which a system like Idai could turn itself around. Cyclone Idai, already described in detail, struck in March of 2019 and stands as the clearest documented case of the channel's re-intensification mechanism in action. A storm that weakened over land, crossed back over deep, eddy-warmed water, and returned to the coast, dramatically strengthened within roughly a day and a half. Idai's death toll across Mozambique, Zimbabwe, and Malawi combined exceeded 1,000 people, with over 1 million more affected, and it triggered one of the largest humanitarian responses in the region's recent history, drawing in agencies from across the world to support a reconstruction effort that, in Beira specifically, is still ongoing years later, with entire neighborhoods rebuilt using stricter building codes designed to better withstand the next storm whenever it arrives. Beyond Beira itself, Idai's rainfall triggered some of the deadliest landslides in the region's recent memory in the mountainous Chimanimani district of eastern Zimbabwe, where saturated hillsides gave way and buried entire settlements with little warning, cutting off roads and communication for days, and complicating an already difficult relief effort split across 3 countries at once. Inside Mozambique, the inland city of Chimoio and the farming town of Nhamatanda, both sitting along transport corridors linking Beira to the interior, found themselves cut off entirely for a period as floodwaters submerged the roads and rail lines connecting them to the coast, turning what should have been a short relief supply run into a logistical problem solved largely by helicopter and, once floodwaters receded enough, by boat. Barely 6 weeks after Idai, while relief efforts in Beira were still very much underway, Cyclone Kenneth struck the far north of Mozambique, near the Cabo Delgado coastline, in April of 2019. Kenneth is notable for a different reason than Idai. It became the strongest tropical cyclone ever recorded to make landfall on the Mozambican mainland, with sustained winds equivalent to a major hurricane, an intensity almost never previously observed this far north along the coast, where cooler waters typically limit how strong storms can become before landfall. Kenneth's arrival caught many communities in the region off guard precisely because this part of the coastline had no recent memory of a storm. This powerful, meaning-building practices, evacuation planning, and public awareness hadn't been shaped by the kind of repeated experience that coastal towns further south, closer to Beira, had already accumulated over prior cyclone seasons. Kenneth also struck an area of Cabo Delgado already grappling with a separate, unrelated humanitarian crisis, an ongoing insurgency that had displaced tens of thousands of people in the years before the storm arrived, forcing the region's aid organizations to run flood and wind damage response operations alongside conflict displacement response at the very same time, in some of the same coastal districts, stretching an already thin humanitarian presence across 2 simultaneous, unrelated disasters. Kenneth's unusual strength at such a northern latitude has been cited by researchers studying the region as an early signal consistent with a warming ocean extending the geographic range over which extreme intensification can occur within the channel, though attributing any single storm directly to long-term warming trends requires caution, since natural year-to-year variability in the channel's eddy field also plays a substantial role in where and when the strongest storms happen to form. The years following Kenneth continued to test the region. Cyclone Cyclones struck central Mozambique in December of 2020, followed only weeks later by Cyclone Eloise in January of 2021, which made landfall again near Beira, a city that by this point had been struck by significant storms in consecutive years, testing the limits of a reconstruction effort still working through the aftermath of Idai. Cyclone Gom followed in March of 2022, striking further north but still within the broader region shaped by the channel's eddy field, once again demonstrating rapid strengthening in its final approach to the coast, flooding areas that had only recently finished rebuilding from prior storms. The most extraordinary case, however, arrived in February and March of 2023, when Cyclone Freddy became, by a wide margin, the longest-lived and one of the longest-tracked tropical cyclones ever recorded anywhere on Earth. Freddy formed off the coast of northern Australia and crossed the entire width of the South Indian Ocean, a journey of well over 5,000 miles, before reaching Madagascar and the Mozambique Channel, a track so unusually long that it forced meteorologists to reconsider assumptions about how long a single tropical system could realistically persist. Along the way, Freddy underwent repeated cycles of intensification and weakening, a behavior almost unheard of over such a sustained period, at one point reaching an estimated accumulated cyclone energy, a technical measure of a storm's total wind energy output over its lifetime, higher than some entire Atlantic hurricane seasons combined. Its final chapter played out largely within the Mozambique Channel itself, where it struck Madagascar, weakened considerably over the island's mountainous terrain, and then, drawing on exactly the kind of deep, warm water and favorable upper-level conditions described earlier in this story, re-intensified sharply before making a first landfall in Mozambique, near the city of Quelimane. Remarkably, Freddy then looped back out over the channel a second time, an almost unprecedented maneuver for a storm this late in its life cycle, re-strengthened yet again, and made a second, separate landfall days later, ultimately striking Mozambique and Malawi with catastrophic flooding that killed well over 500 people, many of them in landslides triggered by the storm's extraordinary rainfall totals across Malawi's highlands, where entire hillsides gave way under the saturated ground, burying homes and roads beneath layers of mud and debris. In the southern Malawian city of Blantyre, entire hillside neighborhoods built on steep, informally settled slopes were among the hardest hit, a pattern disaster researchers had already flagged as a growing risk in the years before Freddy arrived, as rapid urban growth had pushed housing onto slopes never intended to hold dense settlement, slopes that Freddy's rainfall, among the heaviest ever recorded from a single tropical cyclone anywhere in the world, simply couldn't hold in place. Search teams spent days afterward working through collapsed hillsides by hand in places heavy machinery couldn't reach, a grim, painstaking process that underscored how much of the damage from a storm like Freddy has comparatively little to do with wind at all, and almost everything to do with where and how people have had to build their homes on land that offered few genuinely safe alternatives. Freddy's overall lifespan, stretching across more than 5 weeks from its formation off Australia to its final dissipation over southern Africa, was long enough that the World Meteorological Organization's Regional Committee later retired the name permanently from the basin's list. The same formal designation given to Idai 4 years earlier, a quiet acknowledgement that both storms had crossed a threshold of destruction severe enough that the name itself needed to be set aside. Researchers who studied Freddy's track in detail after the fact noted that its behavior within the Mozambique Channel, specifically the sharp re-intensification following its first weakening pass over Madagascar, tracked closely with the position of a warm core eddy sitting almost directly in its path. One more entry in a growing catalog of individual storms whose sudden strengthening lines up, case by case, with the eddy field described earlier in this story, rather than with any change in the broader atmospheric pattern above it. Freddy's repeated re-intensification within the Mozambique Channel, cycle after cycle, over the course of more than a month, stands as perhaps the single clearest illustration available anywhere in the observational record of just how reliably this particular channel can rebuild a weakening storm, almost as if the water itself refuses to let a system die quietly, feeding it again and again, until it finally exhausts every favorable eddy in its path and runs out of coastline left to strike. Why does the Mozambique Channel behave so differently from the ocean basins most familiar to a global audience, chiefly the Atlantic, home to hurricanes that regularly threaten the United States and the Caribbean, and the Western Pacific, home to the most powerful tropical cyclones recorded anywhere on the planet? The Atlantic basin is enormous by comparison, and storms crossing it spend much of their lives over water that varies considerably in both surface temperature and subsurface heat content, depending on the exact path a storm happens to take across the basin. Saharan dust outbreaks periodically inject dry, stable air into the eastern Atlantic, suppressing development for days or weeks at a time, something the Mozambique Channel's shorter, more consistently moist atmospheric environment rarely experiences to the same degree given its comparatively small size and its position tucked away from the kind of continental dust sources that regularly affect the tropical Atlantic. Atlantic hurricanes also frequently encounter higher and more variable wind shear, particularly during years when broader climate patterns like El Niño favor stronger upper-level winds across the basin, patterns that can suppress an entire hurricane season's activity, almost regardless of how warm the ocean happens to be that year. Much of the Atlantic's open water also lacks the kind of persistent, deep, eddy-driven heat reservoirs that define the Mozambique Channel, with one notable exception worth naming directly: the Gulf of Mexico's loop current. Itself famous among meteorologists for its own eddy-driven rapid intensification events. That same mechanism, deep warm water resisting storm-driven mixing, fed Hurricane Katrina's rapid strengthening in the Gulf before its catastrophic landfall on the United States Gulf Coast, and it has since been documented feeding numerous other Atlantic hurricanes that crossed directly over loop current eddies on their way toward landfall, a striking parallel to what happens routinely in the Mozambique Channel. Researchers comparing accumulated cyclone energy, the running total of wind energy a storm generates across its entire lifetime, across different basins, have found that while the Atlantic and Western Pacific together account for the large majority of that energy produced worldwide in any given year, simply because they produce so many more storms overall, the Southwest Indian Ocean Basin punches well above its numerical weight when measured storm for storm, with a comparatively high proportion of its systems reaching intense status at some point in their life cycle relative to the total number that form, a statistic consistent with everything described earlier about how reliably this channel's combination of deep heat and favorable atmosphere pushes weaker systems toward genuine intensity, rather than letting them fade out as ordinary, forgettable storms, the way a similar system might in a less favorable basin. The Western Pacific, meanwhile, holds the largest reservoir of warm ocean water anywhere on Earth, an area so vast and so consistently warm that it's often referred to by oceanographers simply as the warm pool, a region of ocean where sea surface temperatures remain above the threshold needed for cyclone formation across a stretch of water spanning thousands of miles in every direction, essentially year-round. This basin produces the most intense tropical cyclones recorded anywhere, with wind speeds that can exceed anything ever documented in the Mozambique Channel. Storms like Typhoon Haiyan, which struck the Philippines in November of 2013, with sustained winds among the highest ever recorded at landfall anywhere in the world, killing more than 6,000 people and demonstrating just how much destructive potential the warm pool's vast, deep heat reservoir can ultimately unleash. In the coastal city of Tacloban, Haiyan pushed a storm surge that residents and even some emergency planners initially mistook for a tsunami, a wall of water reportedly reaching the height of a two-story building in places, catching many people off guard precisely because the term storm surge, translated into local warning language, hadn't conveyed the scale of what was actually approaching, a communication failure that disaster researchers studying the Philippines have since worked hard to correct in subsequent warning systems. But the Western Pacific's sheer size cuts both ways. Storms there often travel thousands of miles across open ocean before ever threatening a coastline, passing through multiple distinct atmospheric regimes along the way, some favorable to intensification, others not, and encountering considerable year-to-year variability in shear driven by competing monsoon and subtropical high-pressure patterns that shift the most favorable conditions around from one part of the basin to another. The Mozambique Channel offers something neither of these larger basins can: compactness. A cyclone entering the channel from the north is, almost by geographic necessity, going to spend a significant portion of its remaining life over water shaped by the same eddy field, under the same seasonal atmospheric regime, before encountering a coastline within a matter of days, rather than weeks. Comparatively little room exists for a storm to wander into unfavorable conditions before making landfall, unlike a Pacific typhoon, which might spend a week crossing open ocean under shifting conditions before ever threatening land. Combine that geographic compactness with a coastline defined by an unusually wide, shallow continental shelf, capable of amplifying whatever surge the storm arrives with, and you get a basin that, while producing fewer storms overall and generally lower peak wind speeds than the Pacific's most extreme typhoons, punches dramatically above its weight in terms of how efficiently a storm's strength translates into destruction on the ground once it finally arrives. A third comparison is also worth briefly considering, one closer in character to the Mozambique Channel than either the Atlantic or the Western Pacific: the Bay of Bengal, another relatively enclosed body of warm water bordered by a low-lying, densely populated coastline prone to catastrophic storm surge. The Bay of Bengal has produced some of the deadliest tropical cyclones in recorded history, including a storm in 1970 that killed an estimated several 100,000 people in what was then East Pakistan and is now Bangladesh, almost entirely due to storm surge, flooding across an extremely low-lying, densely populated delta region with limited warning infrastructure at the time. A more recent example from the same basin, Cyclone Nargis, which struck Myanmar's Irrawaddy Delta in May of 2008, killed well over 100,000 people through storm surge alone, again despite wind speeds at landfall that, in isolation, wouldn't have placed it among the most extreme tropical cyclones ever recorded. In both cases, as in Mozambique, the coastline itself, flat, shallow, densely settled, and laced with river deltas that channel surge inland rather than letting it dissipate, did as much to determine the final death toll as the storm's own wind speed ever did. That comparison underscores a pattern worth naming plainly. The deadliest tropical cyclone disasters in history have rarely come from the single strongest storms on record in terms of pure wind speed. They have come from storms of significant, though not always maximal, intensity striking coastlines shaped in exactly the way that turns ordinary storm surge into a catastrophic wall of water, a description that fits the Mozambique Channel's Sofala coast with uncomfortable precision. No single ocean basin here is simply more dangerous than another in some general, easily ranked sense. Different physical arrangements produce different failure modes, each one worth understanding on its own terms, rather than folded into a single, generic idea of what a dangerous tropical cyclone looks like. The Western Pacific builds the strongest storms on Earth by sheer accumulated exposure to warm water across enormous distances. The Mozambique Channel builds storms that are, on average, less extreme in peak wind speed, but arrive at vulnerable, low-lying coastlines, having had almost no opportunity to weaken, their re-intensification windows compressed into the final day or two before landfall, precisely when there's the least time left for warnings, evacuations, and preparation to catch up with a storm's true strength. A further wrinkle is worth naming here, one that separates the Mozambique Channel from all three of the basins just described. Both the Atlantic and the Western Pacific benefit from mature, heavily resourced national weather services on nearly every coastline they threaten, backed by decades of accumulated public investment in radar networks, evacuation infrastructure, and building codes. Even the Bay of Bengal, despite its own history of catastrophic loss of life, has seen enormous investment in cyclone shelters and community warning systems across India and Bangladesh since the disasters of the 20th century, investment credited with reducing death tolls from comparably powerful storms by orders of magnitude across the decades since. Mozambique, by contrast, remains among the world's less wealthy nations, with a national meteorological service, a disaster management agency, and an emergency response infrastructure that operate with a fraction of the resources available to their counterparts guarding other cyclone-prone coastlines, meaning the physical mechanism described throughout this story lands on a coastline with comparatively less capacity to absorb its consequences, independent of the storm's physics entirely. For all that scientists now understand about the mechanisms driving rapid intensification in the Mozambique Channel, a significant blind spot remains, and it sits less in the physics of the ocean and atmosphere than in the practical difficulty of observing this particular stretch of water in real time, with the kind of continuous, high-resolution data that forecasters in other parts of the world often take for granted. In the Atlantic Basin, hurricane forecasters have access to a resource unmatched anywhere else in the world: dedicated reconnaissance aircraft, flown directly into storms by agencies including the United States Air Force Reserve and the National Oceanic and Atmospheric Administration, dropping instruments directly into a storm's core to measure pressure, wind speed, and structure in real time, providing forecasters with ground truth data that satellite estimates alone can't match. No equivalent aircraft reconnaissance program exists for the Southwest Indian Ocean. Forecasters responsible for the Mozambique Channel, operating primarily through Meteo France's regional center on Reunion Island, the officially designated regional specialized meteorological center for this basin under World Meteorological Organization protocols, rely almost entirely on satellite-based estimates. A combination of infrared and microwave imagery interpreted using techniques like the Dvorak method, a system developed in the 1970s by an American meteorologist studying satellite imagery of tropical systems, which estimates a storm's intensity by comparing its cloud pattern, the curvature of its banding, the symmetry of its central dense overcast, the clarity of its eye, once one forms, against a standardized set of reference images calibrated over decades against storms whose intensity was independently confirmed through other means. Most often aircraft reconnaissance in basins where that resource exists, along with scatterometer-derived surface wind estimates from polar orbiting satellites that may only pass over any given storm a couple of times a day, leaving long gaps during which a storm's true intensity can shift substantially without anyone directly observing the change as it happens. The surface observation network across the Southwest Indian Ocean compounds the problem further. Weather buoys, the moored instruments that provide continuous ground truth readings of wind speed, pressure, and wave height in many other ocean basins, are sparse across this stretch of water compared to the dense buoy networks maintained across the Atlantic and parts of the Pacific, largely a function of cost and the logistical difficulty of maintaining equipment across such a remote, sparsely serviced stretch of ocean. Occasional dedicated research cruises have ventured into the channel specifically to deploy temporary instruments and validate satellite-derived heat content estimates against direct measurements, and these campaigns have proven valuable precisely because they're so rare, each one adding a small but meaningful correction to models that otherwise rely almost entirely on remote sensing. Commercial shipping routes through the channel provide occasional supplementary weather reports as vessels pass through, a resource meteorologists in this basin have learned to make use of despite its inconsistency, but nothing resembling the dense, continuous coverage available to forecasters watching the Gulf of Mexico or the Northwest Pacific. This matters enormously for a phenomenon defined by speed. Rapid intensification, by definition, unfolds over a period as short as 24 hours. A satellite that captures a storm structure once every several hours, rather than continuously, can miss the earliest signs of an eye wall tightening or a pressure gradient steepening, meaning that in many documented cases across this basin, the confirmation that a storm has undergone rapid intensification arrives only after the process is already well underway, sometimes only in the hours immediately before landfall, leaving forecasters and coastal communities working with warnings that consistently lag just behind reality rather than ahead of it. A genuinely difficult position for anyone trying to issue an evacuation order with enough lead time for it to actually matter. Evacuation itself is rarely a simple matter of telling people to leave and having them go. Roads in low-lying parts of Sofala province can become impassable well before a storm's strongest winds even arrive. As rising river levels cut off the same routes, people would need to reach higher ground, meaning an evacuation order issued even a day too late can leave a community with genuinely nowhere safe left to travel to, forcing families to shelter in place in structures never designed to withstand what's coming. A deeper scientific question also remains, one that researchers studying this channel haven't fully resolved. Precisely how and when a cyclone's track interacts with the shifting, semi-independent field of eddies churning beneath it. The eddies themselves are reasonably well mapped using satellite altimetry, updated regularly enough to give forecasters a general sense of where the warmest, deepest pockets of heat are located at any given moment. But predicting exactly how a specific storm structure will respond to crossing a specific eddy, how quickly the ocean's stored heat translates into a measurable jump in wind speed, and how sensitive that response is to a storm's exact track relative to an eddy center rather than its edge, remains an active area of oceanographic and meteorological research, not a settled science. With a clean, reliable formula forecasters can simply plug numbers into. Small shifts in a storm's forecast track, well within the normal margin of error for cyclone forecasting even several days out, can mean the difference between passing near the edge of a warm eddy and crossing directly over its energetic core, with dramatically different consequences for how strong the storm becomes before it reaches a coastline that, in many cases, has only days or even hours to prepare once the picture becomes clear. Even the basic question of how many named storms will form in a given season carries wider error bars in this basin than forecasters would like, since the seasonal outlooks issued each year by regional climate centers depend on statistical relationships built from a comparatively short historical record, only a few decades of reliable satellite-era observations. Compared to the far longer instrumental records available for the Atlantic, a short record makes it harder to distinguish a genuine shift in the channel's behavior. Whether from natural multi-decade climate cycles or from long-term warming, from ordinary statistical noise, one more way in which this basin's scientific understanding, while substantial, still trails what forecasters in more heavily monitored parts of the world can offer. This gap between what science understands about the general mechanism and what forecasters can reliably predict about any single storm's specific behavior is the unresolved boundary sitting at the heart of this entire story. The Mozambique Channel's physics are, by now, reasonably well explained, a far cry from how the channel might have been described only a few decades ago, before satellite altimetry and ocean profiling floats gave researchers a real window into what was happening beneath the surface. Every major ingredient, from the eddy field to the wind shear windows to the shallow continental shelf, has been documented, measured, and connected to real storm behavior through years of dedicated research published across meteorological and oceanographic journals. What remains genuinely difficult is translating that general understanding into precise, reliable, storm-by-storm warning with the kind of lead time that a coastline like Mozambique's, largely without the reconnaissance infrastructure available elsewhere in the world, urgently needs. And closing that gap remains an ongoing project rather than a finished one. While the forecasting science keeps working to close that gap, the coastline it's meant to protect keeps living with the storms that already arrived. Beira, more than 7 years after Idai, and only a few years after Freddie revisited nearly the same stretch of coastline, remains a city defined by its relationship to this channel. It sits low, much of it barely above sea level, built on land shaped by exactly the same river deltas and shallow coastal geometry that make it so vulnerable to storm surge in the first place. A settlement whose entire history, dating back to its founding as a Portuguese colonial port, has been shaped by its position at the mouth of the Pungwe River. More than 500,000 people live there, with hundreds of thousands more spread across the surrounding lowlands of Sofala province, in towns and villages along the Pungwe and Buzi rivers that flood with a regularity most of the world would find almost unimaginable, a rhythm of seasonal risk woven so deeply into daily life that it shapes decisions most people elsewhere would never have to think about at all. From which season to schedule a wedding around, to which materials are worth using on a roof that might need replacing again within a handful of years, regardless of how well it's built. In the years since Idai, the response hasn't simply been to rebuild what existed before, replacing damaged structures with identical replacements in the same vulnerable locations. With support from international partners, including the World Bank, Beira has invested in expanded stormwater drainage systems designed to move floodwater out of the city more quickly once heavy rain arrives, reducing the standing water that can turn an already dangerous flood into a prolonged public health crisis. The city has also invested in restoring stretches of mangrove forest along the coastline, a natural buffer that had been cleared in earlier decades for development and aquaculture. But that research consistently shows can meaningfully reduce the destructive force of storm surge before it reaches populated areas, absorbing wave energy and slowing the inland push of water through a dense tangle of roots that engineered infrastructure alone can't fully replicate. Local nurseries have been established specifically to grow mangrove seedlings suited to the particular salinity and sediment conditions of the Pungwe estuary, with planting efforts often organized around school groups and community volunteers, rather than contracted labor alone, an approach that doubles as a way of building local investment in protecting the coastline that these same volunteers and their families depend on every single cyclone season. Early warning systems have also been strengthened, with community-level networks designed to translate national and regional cyclone bulletins, often issued in technical language from meteorological centers hundreds of miles away, into clear, local guidance that reaches people without reliable access to television, internet, or even consistent electricity. Using methods as simple as community radio broadcasts and volunteer networks who go door to door in the days before a storm's expected arrival. The mangrove restoration work in particular has drawn attention from coastal engineers well beyond Mozambique, since it represents a comparatively low-cost intervention with benefits that extend beyond storm protection alone. Restored mangrove stands along the Beira coastline also support fish nurseries and provide a buffer against the slower, less dramatic erosion that steadily eats away at unprotected coastline even outside cyclone season, meaning the investment pays off in ordinary years as well as catastrophic ones. Community-based cyclone shelters, often built to elevated, reinforced standards well beyond typical local construction, have also been expanded across Sofala province in the years since Idai, giving families in low-lying villages somewhere safe to move to on short notice rather than facing the impossible choice between an unsafe home and an evacuation route that floodwater might cut off entirely before they can reach safety. None of this makes the underlying threat disappear. Freddie's arrival in 2023, striking a region still actively rebuilding from Idai 4 years earlier, was a stark demonstration that the Mozambique Channel doesn't wait for coastal communities to fully recover before sending the next storm. For families living along the Sofala coast, cyclone season isn't a distant abstraction discussed in meteorological journals or international news broadcasts. Cyclone season instead becomes a recurring feature of daily life, one that shapes decisions about where to build a home, what crops to plant and when, how much to invest in structures that might be destroyed again within a few years, regardless of how carefully they're built, and how to raise children who'll grow up needing to understand this rhythm just as well as their parents and grandparents did. A psychological weight comes with that repetition. One disaster researchers studying the region have only recently begun to document with any rigor, distinct from the physical damage a storm leaves behind. Communities that rebuild after one major cyclone only to be struck again within a few years describe a particular kind of exhaustion, a sense that recovery is never really finished, that resources and labor poured into repairing a home or a school might need to be poured in again before the debt of the last repair has even been paid off. 8 organizations working in Sofala province have started incorporating mental health and psychosocial support into their standard response alongside food, shelter, and medical care, a recognition that the accumulated toll of repeated disaster runs deeper than counting how many buildings fall down each time, extending into what it costs a community to keep standing back up. A particular kind of resilience is visible in these communities, worth naming honestly, without romanticizing hardship that shouldn't have to be endured in the first place, and without suggesting that resilience is any substitute for the infrastructure and warning systems that wealthier regions of the world take for granted. Farmers along the Pungwe and Buzi rivers have developed planting calendars adapted to the near certainty of seasonal flooding, choosing crop varieties suited to waterlogged soil and timing harvests to fall before the heaviest rains typically arrive. Fishing communities along the coast maintain informal early warning networks built on generations of accumulated knowledge about how the sky and sea behave in the days before a major storm arrives, reading subtle changes in swell patterns, wind direction, and cloud formation that have been passed down through families for generations. Knowledge that, in many documented cases, has saved lives even when official warnings arrived too late or failed to reach isolated areas at all. None of this substitutes for the kind of forecasting infrastructure available to wealthier coastal regions elsewhere in the world, and it shouldn't have to. But it represents a genuine, adaptive response to living permanently downstream of a storm intensification engine whose stored ocean heat can rival the Western Pacific's warm pool, the largest reservoir of cyclone fuel on Earth, a response built out of necessity rather than choice. The economic toll of repeated storms falls hardest on exactly the people least equipped to absorb it. Small-scale fishing crews along the Sofala coast frequently lose boats, engines, and nets to major cyclones, equipment that represents a household's entire working capital and that often can't be replaced without outside assistance, meaning a family's ability to earn a living can remain crippled for a full season or more after the physical floodwaters have already receded. Subsistence farmers along the Pungwe and Buzi rivers face a related problem. Floodwaters that arrive during the growing season can wipe out an entire harvest at once, and because so many households in the region depend on what they grow both to eat and to sell, a single storm arriving at the wrong point in the agricultural calendar can produce food insecurity that lingers for months, long after the storm itself has become old news everywhere outside the region it struck. A broader question sits underneath all of this, one that connects the Mozambique Channel to a much larger system. What happens to a mechanism like this one as the ocean itself continues to warm? A question that matters not just for this specific stretch of coastline, but for every coastal region on Earth, shaped by a comparable combination of deep, warm water and vulnerable, low-lying land. The physical relationship described throughout this story, deep ocean heat content enabling rapid intensification by removing a storm's natural self-limiting break, exists elsewhere in the world's oceans too, and it becomes more consequential everywhere it appears as background ocean temperatures rise across the entire planet. Research tracking ocean heat content across the world's tropical and subtropical oceans has documented a clear long-term warming trend over recent decades, measured consistently by the same network of autonomous profiling floats that oceanographers use to study the Mozambique Channel's eddy field and the southwest Indian Ocean, including the Mozambique Channel specifically. Has been identified in multiple published studies as a region experiencing some of the more pronounced warming trends found anywhere in the Indian Ocean basin, along with an increase in the frequency and intensity of marine heat waves, periods of anomalously warm water that can persist for weeks or months at a time, and that researchers have increasingly linked to the same broader pattern of ocean warming documented across the globe. Marine heat waves in this region carry consequences well beyond cyclone intensification alone, offering a second, independent line of evidence that the channel's waters are shifting. Coral reef systems along the Mozambican and Madagascar coastlines have experienced documented bleaching events during particularly intense marine heat wave years, a stress response in which corals expel the microscopic algae they depend on when water temperatures remain too high for too long, sometimes leading to widespread coral death if temperatures don't recover quickly enough. Scientists monitoring these reefs use them, in effect, as a biological thermometer for the channel, a slower but complementary record running alongside the satellite and float-based measurements described earlier. And the trend visible in both records points in the same direction. Global studies of tropical cyclone behavior across multiple ocean basins have found a documented increase over recent decades in the proportion of storms that undergo rapid intensification, alongside research suggesting that the upper bound of how intense a rapid intensification event can become has also been rising in step with ocean warming, a trend consistent with the basic physics described throughout this story. Warmer water, all else being equal, holds more of the deep, storm-resistant heat that fuels this kind of explosive strengthening. Climate scientists modeling the region's future rely on a technique called downscaling, in which the broad, coarse projections produced by global climate models, which typically represent the entire Mozambique Channel as only a handful of grid points, get refined using higher-resolution regional models capable of capturing the channel's specific geography, its narrow width, its position relative to Madagascar, and its seasonal atmospheric patterns, in far greater detail than a global model ever could on its own. These regional projections carry more uncertainty than researchers would like, particularly regarding exactly how the eddy field itself might respond to a warmer background ocean, since eddies are a comparatively small-scale feature that global models struggle to represent accurately even today. But the broader direction embedded in nearly every version of these projections points the same way: a warmer channel, a deeper reservoir of storm fuel, and a coastline that will need to plan for storms behaving, on average, less like Helene in the year 2000 and more like Freddie in 2023. Individual storms can't be attributed directly to climate change in a simple, one-to-one sense, since natural variability, driven by factors like the eddy field's own semi-random timing and the Madden-Julian oscillation's unpredictable pulse, will always play a substantial role in any single storm's behavior. And researchers are careful to distinguish between a long-term statistical trend and any individual event. But the broader pattern, a warming ocean providing deeper, more persistent reservoirs of stored heat across more of the world's cyclone-prone waters, points toward conditions that make the specific mechanism driving storms like Idai, Kenneth, and Freddie more common rather than less, not just in the Mozambique Channel, but in comparable coastal regions worldwide, from the Gulf of Mexico to the Bay of Bengal to the waters off the Philippines. A second, compounding factor is worth naming honestly: sea level rise. As global sea levels continue to climb, even gradually, every storm surge that reaches a coastline like Beira's begins from a higher baseline than it would have a few decades earlier, meaning that a storm producing a surge of comparable height to Idai's, arriving at a coastline decades from now, would push water further inland and affect more people and more infrastructure than the same storm would today, even without any change in the storm's own intensity. Combined with a continued trend toward more frequent, rapid intensification, driven by a warming ocean feeding the same eddy mechanism already documented across this channel, the practical result for coastal communities is a steady raising of the baseline risk against which every future cyclone season will be measured. A slow ratcheting upward of the stakes that becomes clear only when looking back across multiple decades of storms, rather than any single season in isolation. None of this changes the fundamental mechanism described throughout this story. The Mozambique Channel doesn't need a warming climate to produce rapid intensification. It has been doing so for as long as the region's ocean and atmospheric patterns have existed in their current configuration, almost certainly for thousands of years, before any instrument ever measured it, long before the city of Beira existed at all. What a warming ocean appears to be doing, based on the evidence currently available from decades of satellite and float-based observation, is amplifying a mechanism that was already there, deepening the reservoirs of heat that fuel it, and raising the water that ultimately carries its consequences ashore, turning an already dangerous natural feature of this coastline into a gradually more dangerous one. Scientists studying this trend are careful, appropriately, not to overstate what any single future season will look like, since the channel's eddy field, the monsoon trough's exact timing, and the Madden-Julian oscillation's unpredictable pulse will all continue to introduce genuine year-to-year variability, regardless of the underlying warming trend running beneath them. What the accumulated evidence does support, drawn from decades of satellite altimetry, thousands of profiling float measurements, and a documented rise in both ocean heat content and the frequency of marine heat waves across the southwest Indian Ocean, is a shift in the odds rather than a certainty about any individual storm. A coastline that already sat downstream of a rapid intensification engine efficient enough to rival the Gulf of Mexico's loop current is, by the best available evidence, facing a version of that engine running somewhat hotter than it did when Helene struck in the year 2000, a difference too gradual to notice from one cyclone season to the next, but significant when the record is viewed across the full span of decades now available to researchers. What makes the Mozambique Channel worth understanding goes beyond the simple fact that it produces dangerous storms, something plenty of ocean basins do. This particular stretch of water offers something close to a complete visible case study in exactly how a tropical cyclone actually works, stripped down to its essential mechanism and laid bare by geography that concentrates every ingredient into an unusually small, unusually well-documented space. Think back to where this story began, with a storm doing something that looked, on the surface, like it broke the ordinary rules of how weather is supposed to behave. A weakening system responds to what's beneath it when it reverses course and comes back stronger, the same way any physical system responds to the specific conditions it encounters, and the fact that those conditions happen to be arranged so favorably, so completely, in this one particular channel isn't an accident of storytelling. Currents have been circulating in roughly this configuration for longer than any human coastline has existed nearby to be threatened by them. The warm core eddies spinning south from Madagascar, carrying pockets of deep heat down the length of the channel on their own independent schedule. The seasonal window of low shear and favorable upper-level outflow opened and closed by the rhythm of the intertropical convergence zone and the Madden-Julian oscillation passing overhead. The wide, shallow shelf waiting at the coastline to turn wind energy into a wall of water the moment a storm finally arrives. Each piece traceable, each piece measurable, and each piece playing out again and again across decades of storms that scientists have been able to study in remarkable detail, from Helene in the year 2000 through Idai, Kenneth, and Freddie in the years since. Picture one last time the arc this entire story has traced. It began with disbelief, a storm that should have died quietly instead, coming back from the edge of dissipation to devastate a city. It moved into mechanism, first the ocean's hidden architecture of eddies and stored heat, then the atmosphere's seasonal cooperation, then the coastline's own geometry, waiting to turn wind into a wall of water. It moved through the evidence, a documented sequence of storms stretching back decades, each one confirming the pattern a little more precisely than the last. And it arrived, finally, at the honest edge of what's still unknown, the gap between understanding a mechanism in general and predicting any single storm's behavior with the precision a threatened coastline actually needs. That arc, from an impossible-looking event to a fully explained, still imperfectly predictable system, isn't a story confined to this one channel. Science understands almost anything that once looked like magic this same way. It turns out, on closer inspection, to be physics operating exactly as it should, just previously unseen. The storm that opened this story, tearing itself apart over the hills of central Mozambique before turning back to the sea and rebuilding itself into something far more dangerous within a day and a half, wasn't behaving mysteriously, even though it looked that way from the outside. Even though it defied the intuitive expectation that a weakening storm should simply continue to weaken. It was responding with almost mechanical precision to a set of physical conditions that researchers have spent decades mapping, measuring, and connecting to real catastrophic outcomes on the ground. Understanding that mechanism won't stop the next cyclone from forming, and it won't by itself protect a single home along the Pungwe River, but it's, quite directly, the foundation on which every improvement in warning time every refined forecast model, and every meter of restored mangrove coastline ultimately depends. Work that's happening right now in Mozambique and in research institutions around the world aimed at closing the gap between how well science understands this channel's physics and how much lead time it can actually give the people living in its path. A kind of quiet dignity runs through that ongoing work, one that rarely makes it into the coverage a major storm receives once it has already struck. Long before Idai formed, before Kenneth caught the north of Mozambique off guard, before Freddie looped back across the channel a second time, researchers were out on ships in this water, dropping instruments over the side, waiting weeks for data to accumulate, comparing satellite estimates against direct measurements, one profile at a time. None of that work generates the kind of footage that circulates widely once a cyclone makes landfall: the flooded streets, the collapsed roofs, the rescue helicopters. But it's the reason forecasters today can say with real confidence that a specific eddy sitting in a storm's path raises the odds of rapid intensification, rather than simply watching, as earlier generations had to, and hoping a weakening storm stayed weak. Every additional profiling float deployed, every additional satellite pass processed, every additional season of storms folded into the historical record narrows the gap this story has spent so much time describing, one careful measurement at a time. In water, most of the people it will eventually protect will never see or think about directly. That gap between a mechanism scientists can already explain and a warning a family can actually act on keeps narrowing only when more people stay curious about how storms like Idai actually work. And a small amount of support goes further towards that than it might seem. Subscribing means the next storm gets traced with this same care, mechanism by mechanism rather than just wind speed and a death toll. A like helps too, quietly, by putting a story about thermoclines, shallow continental shelves, and a rebuilt city on the Pungwe River in front of people who have never heard of Beira at all. One question is worth answering honestly in the comments rather than scrolling past it. Picture living on the Sofala coast, in a town that has already rebuilt after Aline, Idai, and Freddie. Would a day and a half of warning, roughly what Idai actually gave Beira before its second landfall, be enough time to get your family somewhere safe? Or would you already be moving the moment the sky started behaving wrong, official warning or not? Say which and say why in the comments below. The Mozambique Channel isn't finished building storms out of water most of us will never see the bottom of. And the work of explaining clearly how it does it isn't finished either.